Yep, I've started the recording.
All right. All right, so good afternoon, everyone, and thank you for joining me today. So today I'll be talking about VTR8 and some of the other research that I've done in the FPGA CAD space. And so a little bit of background about me. So I'm Kevin Murray, and I'm a PhD candidate at the University of Toronto, supervised by Von Betts. And I'm almost finished graduation. And I'm currently working at Cerebras Systems in Toronto. So let's dive in and get started. Okay, so to start off, just to make sure that we're kind of all on the same page, I just want to go over some FPGA basics. So an FPGA is a microchip that has programmable hardware. So at the most basic level, we have things like lookup tables that can implement kind of arbitrary combinational logic, and flip-flops that allow us to store sequential state, and some amount of connectivity that's configurable to connect these all together. And by having a large number of these, we can implement an arbitrary digital circuit on our FPGA. Once we have that basic logic element, in the FPGA architecture, these tend to be grouped together into logic blocks, so a collection of logic elements. And then these get tiled out onto the actual FPGA device grid. So we have a grid of logic blocks and potentially other blocks like RAM blocks or DSP blocks, along with interconnect wires that go between them and interconnect them. And these interconnect wires have routing switches that we can configure to connect these different blocks together. So that's kind of at a high level the FPGA hardware. If we want to actually take an application, so say that you're doing some genome sequencing or a machine learning inference accelerator, how do you actually program the FPGA to implement that circuit? So the way we do this is with an automated CAD flow. So modern FPGAs are extremely large. I think the largest Stratix device is on the order of 10 million logic elements. So it's really infeasible to do this design by hand. So what we use is this automated design flow where the designer provides us a high-level behavioral specification in some kind of hardware description language. And then we have a variety of algorithms and tools that process that high-level behavioral specification and figure out all the low-level details that are required to produce the final bit stream that actually configures the FPGA to implement our design. Okay, so that's kind of a high-level overview of FPGAs. Now I want to talk a little bit about some types of FPGA research questions or research areas. So one thrust of FPGA research is architecture research. This is basically where we have an FPGA architecture and we want to make some change to it to perhaps improve its power consumption or improve its performance or reduce its area. So these are all kind of architectural questions of how do we actually build FPGA hardware to be efficient. And so this is a challenging problem for a couple different reasons. First off, there are effectively no closed form solutions for kind of evaluating how good an FPGA is. And as a result, we take a kind of empirical research approach where we take some set of benchmark designs that are representative of the kind of applications that we care about. And we have, several candidate FPGA architectures, perhaps variations of a baseline architecture, or just drastically different architectures. And we want to kind of measure what kind of speed, area, and power these architectures are capable of. Now, to do this, we have to map each of these benchmarks to each of these different FPGA architectures. Which means that we need an FPGA architecture that can target, a CAD flow that can target each of these different FPGA architectures. And additionally, that CAD flow needs to be of high quality so that we're kind of sure that when we map the benchmarks to that architecture, we're kind of getting a good implementation and hence a good measurement of how good that FPGA architecture itself is. So another thrust for research is actually research in the FPGA computer-aided design flow itself. So as I showed before, this design flow is relatively complicated, and there are lots of interlinking stages that all depend upon each other. And so if you're a CAD researcher, you probably have an idea for one specific algorithm within this CAD flow. And so it would be extremely time consuming to go and build this CAD flow from scratch just to go and evaluate your one idea. So it would be very helpful for the research community and more productive for researchers individually to use some kind of shared common infrastructure and not have to rebuild this CAD flow from scratch. Additionally, this kind of reference CAD flow would provide you kind of with good best practices, kind of good methodologies for running experiments, and importantly, would also allow you to compare to other published research results. A third kind of issue that can come up is if you have some kind of new novel spatial compute architecture. Maybe you've built it and actually fabbed it. Maybe it's an FPGA, maybe it's an FPGA combined with something else or some other new type of novel spatial compute architecture. But to be able to program this, you have to have a CAD flow. So this kind of CAD flow kind of becomes the crux for these three kind of different areas of FPGA and spatial computing research. And to kind of give you a feel for kind of what kind of novel spatial compute architectures are out there, this here is a project from MIT Lincoln Lab called Reimagine. It is a custom FPGA that they've actually gone and fabbed, and they are stacking on top of it different types of optical detectors, and with all the signal processing happening in the underlying FPGA. And there are also projects like the Open FPGA project from the University of Utah and the PRGA project from Princeton that are designing and fabbing their own FPGAs. So this kind of need for an FPGA CAD flow that is flexible and something that we can go in and change is some of the main motivators for the Verilog to Routing or VTR project. So VTR is an open source FPGA CAD flow, and it's really aimed at supporting FPGA architecture research and computer-aided design, algorithm and tool research. And the way this CAD flow works is we have a Verilog description of the circuit. We pass it through a tool called Odin to kind of synthesize that into Boolean logic equations. These logic equations are then optimized and technology mapped by a tool called ABC from the University of Berkeley. And this then feeds into VPR, which is the tool that does placement and routing to kind of produce the final design implementation. And so what makes VTR unique is that we take what's called an architecture agnostic approach. So instead of kind of hard coding the details of the different FPGA architectures into the tools themselves, we instead have this FPGA architecture description file that describes in a data-driven way what the FPGA architecture is. And that data-driven description is used to drive all of the different optimization stages. And so this gives us a lot of great flexibility in being able to target different FPGA architectures. So VTR as a project kind of faces a couple different challenges. First off, we want kind of architecture generality. We want to be able to explore a larger design space of hypothetical FPGA architectures, which means the tool needs to be very flexible and not hard code many assumptions about the architectures that it's targeting. But in order to kind of trust our architectural conclusions, we also really want to make sure that we produce a high quality implementation for any architecture that we target. And if you're kind of in the design implementation flow where you're a designer trying to map an application to this architecture, you also want high quality CAD flow so that you can spend less time tuning and optimizing your design. And then finally, we want both of those things, but we also want our runtime to be reasonable. Since the FPGA CAD flow is already very time consuming, taking on the orders of hours to days for very large designs. And so the thrust of my research has largely been, how can we find trade-off points that allow us to have all three of these characteristics? And that's what I'm going to talk about today as I go through some of the features that are in the VTR8 release. So here's the kind of rough outline for what I'm going to go through in the remainder of this talk. I'll start off by talking about some of the capabilities and new features that are included in VTR8. I'm then going to kind of dive in depth on one of the optimization stages, in this case, the router and the adaptive incremental router or AIR algorithm that we use in VTR8. I'll then pop back out and take a look at kind of the overall quality of result and runtime, as well as some of the other CAD enhancements that went into VTR8. And then finally, I'll take a look at how we can apply reinforcement learning in placement, which is another kind of optimization stage in the VTR tool flow. Okay, so let's start off by taking a look at some of the features and capabilities in VTR and new features in VTR8. So the core feature in VTR that allows us to have this kind of architecture generality is in the kind of the low-level block modeling. So VTR supports kind of arbitrary logic primitives. So if you want lookup tables, we can support different sizes of lookup tables in your whatever FPGA architecture you're targeting. If you want something that's even not a lookup table, maybe it's some other type of logic element, you can also support, that is also supported in VTR. We can then group these into logic elements, and you can vary things like how many flip-flops there are or whether you have hardened arithmetic inside the logic element. We can vary things like the size of the logic block, so how many logic elements are in a logic block. And we can also give the architect lots of flexibility in choosing how these elements interconnect with each other. And we also support kind of arbitrary hard blocks, so you can have RAM blocks of arbitrary sizes, DSP blocks of kind of however you want to configure them, or other potential blocks as well. And this gives the architect lots of flexibility to define the FPGA architecture that they want to evaluate. So an area that we really focused on in VTR8 was improving the generality of the device grid. This is basically how flexible are we at specifying where the different blocks are located in the FPGA architecture. And so we can support things like blocks around the perimeter at specific locations. We can fill a whole region with a certain type of block. You can arrange things in columns and rows and kind of whatever type of pattern that you wish. And so this allows us to capture, some of the realities that show up in more commercial-like architectures, rather than the kind of simple column-based architectures that many academics have focused on traditionally. And so here's an example that kind of uses some of these features. So we have a small FPGA with IOs around the perimeter. We've got columns of RAM blocks and columns of DSP blocks. We've got a hardened PCIe interface in the bottom right corner. And we also have network on chip routers kind of spaced throughout the fabric. And so this is the kind of architecture that you can now describe in VTR8, with what you weren't able to do in the previous release. So VTR also has a very detailed model of the FPGA routing architecture. So this is the kind of the wires and switches that are used to interconnect the different blocks together. And so we can see in this image, we've got a bunch of routing wires running horizontally and vertically in our FPGA between the blocks. And we support, you can vary the channel widths, and you can also configure things like the input connection block pattern, so how the block input pins connect to the wires that pass by them, how the block output pins connect to wires nearby. We can support things like direct connections between adjacent blocks. And we also give the user significant control over how the wires themselves interconnect together, the so-called switch block pattern. And this information is used to kind of drive the FPGA architecture evaluation, so calculate things like the area of the routing network, and is also used to kind of drive the routing optimization stage as well. And so we made a bunch of enhancements to this in VTR8. You can now customize where switch blocks are located. So if you have something like a large hard processor system in your FPGA and it uses all of the metal layers, so you don't want any switch block switches within that block, you can basically specify and control that at a much finer level of flexibility than you were previously. We also have improvements to the kind of wire connectivity pattern. So you can specify different types of wires and you can change how those different types of wires interconnect to each other to build your routing architecture. We also support things like what we call non-configurable edges. These are basically an elegant way to support things like inline buffers, like what you might find in a clock network, or things like wires that have bends and are not straight lines, so L's and T shapes, like you might find in some commercial architectures. So if those kind of customizations of the routing architecture are actually not quite enough for what you want to do, we've also added support for loading the routing architecture explicitly from an external file. This is what we call an RR graph file. And this file can be either generated by VPR from an architecture that you've provided, or it can come from be generated by some other tool that's not VPR. This gives the end user kind of full control over the routing network that we are operating on. And it allows you to do things like freeze the RR graph if you've actually gone and fabbed the chip, or if you've fabbed a chip and you want to kind of import that routing architecture into VPR, you can just write an RR graph file that represents that and load it into the tool. We also made enhancements to the analysis and modeling capabilities of VTR. So you can now do things like run analysis independent of optimization. We provide much more detailed reporting and visualization. So we now give you, fully detailed timing reports. You can do things like visualize where the critical path is and what routing resources they use. You can look at things at like how many routing resources are being used in certain regions in the device. And we've significantly improved some of the modeling capabilities and things like the area model. And we now support much more full-featured timing analysis, so we can do both minimum and maximum delay timing and support things like multi-clock primitives, which are all things that you need to kind of support if you want to consider more modern FPGA architectures. Okay, so that's kind of the high-level overview of the features in VTR. So now I'm going to kind of dive deep on one of the particular algorithms inside VTR that I worked on, which is the routing algorithm. Okay, so the FPGA routing problem, basically, we start with the FPGA routing architecture. So this is kind of what the user has described to VTR. You have some blocks, they have pins, they connect to some wires, and they connect to each other. So the routing problem, we formulate this routing architecture as what we call a routing resource graph. This is a graph where the nodes correspond to pins and wires, so conductors, and the edges represent configurable switches that we can turn on to connect these conductors together. So the FPGA routing problem then is, given some circuit netlist, we need to find an embedding of the connectivity of that netlist within the routing resource graph. And what this means in practice is we have to find a large number of non-overlapping trees within the routing resource graph. And we need to do that in such a way that we minimize the timing delays and the amount of wiring, which correlates with power. And we need to do that optimization all in a reasonable amount of runtime. And so usually this has been solved as a kind of single combined global and detailed routing optimization stage. Okay, so the adaptive incremental router, this AIR algorithm that I'm going to present, falls into the category of what are called negotiated congestion routing algorithms. And so the key insight of negotiated congestion is that it allows multiple nets to use the same routing resource or conductor. This is what we call congestion. So if a node is used by more than one net, but this has a couple of advantages in the formulation. In particular, it means that nets don't block each other as they're being routed. So the core component of a negotiated congestion router is what we're going to call the connection router. So let's suppose that we have a source and we want to find a path that will connect it to a particular sink. So the connection router will search through the routing resource graph to find this kind of path for us. Now in practice, the nets that we're trying to route usually have multiple sinks. So what we do is we invoke the connection router multiple times in order to route a net. allowing the subsequent sinks to expand from the previous routing that has already been found. Now, once we've routed a particular net, we have to go on and kind of route all the other nets in our design. And once we've routed all the nets in our design, we can then evaluate whether our routing is legal or not. And so if we find that there are some nodes that are being used by multiple nets, these are what we call the congested nodes, we rip up the associated nets, increase the cost of those congested resources, and repeatedly repeat this rip up and reroute process until we arrive at a routing solution that is congestion free. And at that point, we've solved the routing optimization problem. Okay, so let's talk about AIR, the adaptive incremental router. So as I said, this is a negotiated congestion router, and it has kind of two key distinctions. The first off is it adapts to the routing problem that it is given. And the second is that it is a lazy router. It tries to avoid doing as much unnecessary work as possible. So let's talk first about how AIR adapts to the routing problem that it's considering. So there are more details in the paper, but what I'm going to focus on here is how we adapt to the actual architecture that we're targeting. So let's again suppose that we have some source S and we want to expand to a target T, and we're considering a path that goes through a candidate node N. So the router has to have some kind of cost function that it uses to rank what paths are worth exploring. And so the cost function that we use is shown here. We have a previous cost from the source S to reach the candidate node N. There's going to be some node cost associated with using the node. And then there is some expected cost estimate to reach the target from that node. We can break down the node cost details. There's something called a base resource cost, kind of the basic cost of using this node. There are the congestion costs I mentioned that increase over time to kind of alleviate congestion. And because we're also trying to optimize timing, we also include a delay term. And we tend to weight the kind of base cost congestion term and the delay by how timing critical this particular connection is. And so AIR is adaptive in two ways. The one I'm going to focus on, though, is the adaptive look-ahead that we use to produce this expected cost estimate. So the kind of key observation we made is that we really want this look-ahead, which kind of helps the router rank which paths are promising. We really want this look-ahead to kind of adapt to the target FPGA routing architecture. So I'm showing an example architecture here. This is a Stratix 4-like architecture. We've got a bunch of logic blocks and a bunch of length 4 wires. These length 4 wires interconnect to the block pins. They also interconnect to other length 4 wires, and they occasionally interconnect to these longer length 16 wires. These long wires tend to be very fast, so they help us travel long distances very quickly. So if you've got a timing critical connection, you really wanted to use these long wires. Now, as I said, VTR is this architecture agnostic tool, so we don't want to kind of hard code this kind of characteristic into the tool. We want to kind of come up with a general method that will work for many different FPGA architectures. This is really challenging, though, because the routing graph that we're dealing with is very large, on the order of millions to tens of millions of nodes and hundreds of millions of edges. So if we are going to kind of build this look-ahead, we have to do it in a very short amount of time. And because this look-ahead is going to be invoked hundreds of millions of times in the router itself, it has to be extremely fast to evaluate. So the approach that we took is that we select a set of candidate locations in the FPGA fabric, and we do an undirected Dijkstra expansion, which allows us to quickly measure the delay and cost to reach various locations a certain distance away from our candidate sample point. This kind of captures the characteristics of the routing graph and allows us to build a fast and more efficient look ahead. And so what these two plots down here are showing is the kind of traditional approach used in VTR, which we're going to call the classic look ahead, and our new enhanced method, which is called the map look ahead. And what these kind of heat maps are showing is the delay to go certain distances. So for instance, if we are on a candidate length 4 wire, the classic look ahead assumes that we're going to remain on that relatively slow length 4 wire all the way to the destination. And so when we go far distance, certain distance delta x, delta y, the delay estimate increases relatively quickly. But for our enhanced look ahead, it has captured the effect of these fast, long wires. So it produces a much lower delay estimate for far distances, which allows us to get much better quality routing for these kinds of connections. So as I mentioned, AIR is also a lazy router, and it has kind of two techniques that allow it to efficiently search the routing graph. So the first one is a technique to handle high fanout nets, and the second one is a technique to reroute congested nets incrementally. So first, let me talk about the high fanout routing. So the observation we made is that when we're routing a high fanout net, this is a net where we have many sinks that we need to connect. Most of the routing is largely irrelevant to any particular sink. So if we are routing from this source S to this target T, most of the previous routing is going to be far away from the target, and it's not really helpful to actually look at it. So the optimization we made is to only consider expanding from routing resources that are spatially nearby the target. And so this ends up working quite well in practice. And so here's an example of these two techniques. So the traditional technique is on the left. And what this plot is showing is this is the FPGA device grid. And the highlighted elements are basically different routing resources that the router explored to route to a sink that is located right here in the center of the chip. So for a high fanout net, in this case, the fanout something like 3,500 sinks, we end up looking at a large fraction of the FPGA routing network. In contrast with our spatial lookup approach, because we know the target that we're trying to reach is very close to the center of the FPGA, we only need to investigate the routing resources that are nearby, and that saves a significant amount of runtime. So the second lazy optimization that we implemented is incremental routing. And this is kind of driven by the observation that for most nets, most of their connections, so source to sink paths, are legally routed quite early in the optimization process. So the optimization we made is that instead of ripping up the entire net, if there's any congestion in it, we only rip up the congested subtrees. So here, let's suppose we're routing from the source A to the targets D, G, H, and F. And we have routed this at one iteration, and we've found that there is congestion at node E. So where traditional methods would rip up all of this routing and start over from scratch, we only rip up the subtree rooted at E. Once we do that, we can then incrementally reroute, and we only have to reroute the sinks G and H. And so this allows us to preserve the routing from A to D and from A to F. Now, one potential challenge of this approach is that it could degrade the critical path delay. So we also have some code that will rip up delay suboptimal connections, which recovers most of that issue. Okay, so let's think about now about how we're actually going to go about and evaluate the quality of AIR, this new routing algorithm. So we're going to evaluate it on the Titan benchmarks. These are a set of 23 large-scale heterogeneous FPGA designs targeting Stratix 4, and they range in size from 90,000 to 1.9 million netlist primitives. And the CAD flow that we're using here is we start with Verilog circuit descriptions, and we synthesize them with Intel's Quartus to a technology map netlist. And that technology map netlist can then be used in VPR to do packing, placement, and routing. And it can also be done in Quartus to have Quartus do packing and placement and routing. And so we're going to make a couple different comparisons. We're going to compare to the router in VPR7. We're going to compare to a more recent academic router called CRoute. And we will also make a somewhat indirect comparison to the commercial Quartus 18 router. Okay, so here are the results on the academic routers. So here what we're showing are several metrics, and we're showing the normalized value where 1.0 corresponds to the result produced by VPR7. And so what we can observe is that AIR is significantly faster at routing than VPR7. So it completes in more than 6 times faster, and it's about 2 times faster than CRoute. From a quality perspective, the improved look ahead helps to reduce critical path delay by nearly 20%. And the improved base costs and look ahead reduced wire length by 15%. So significant runtime improvements while also improving optimization quality. As I said, we can also make an indirect comparison with Quartus. This is an indirect comparison because the numbers that we're measuring for Quartus correspond to a routing done with Quartus's placement, whereas the results we're showing for AIR are produced with a VPR8 placement. But what we can see is that AIR completes routing about 4 times faster than Quartus. And while there is a quality gap, we believe that this is due to the lower quality placement being produced by VPR8. And so to kind of prove that out for you, here we're going to take a look at the kind of initial routing that AIR achieves. So initially, AIR routes in a congestion-oblivious way, which forms effectively a lower bound on the achievable circuit delay. And we're going to compare that to the final congestion-free legal routing that AIR achieves. And so what we can see is that AIR, the critical path delay does not change. So AIR is able to maintain the best case critical path delay across all the benchmarks. And in fact, we actually see that the wiring is reduced because AIR is able to reroute the non-timing critical connections in a more wire length friendly way. So in conclusion on AIR, AIR is this timing driven FPGA routing algorithm. It adapts to the target architecture, and it is lazy. It tries to avoid doing as much unnecessary work as possible. We showed that AIR is more than 6 times faster than VPR and significantly improves optimization quality, and it's about 4 times faster than Quartus. And we saw that it was able to effectively trade off resource usage to resolve congestion. So there are some other enhancements in the paper about how we adapt to congestion and how we can improve routing by doing reconvergent routing. But that's the kind of the high-level overview of the AIR routing algorithm. And I'll note that AIR is the default router used in VPR8.
Sorry, can I ask
Okay, so now that we've kind of, yeah, sure, please go ahead.
Sorry, on the in AIR, do you have a breakdown of where the speed up is coming from for the various optimizations you've done?
Yes, so those details are in the paper. It kind of gives a breakdown of where the benefits come from. I don't have slides on it at the moment.
No problem.
But it's a combination. In some ways, they stack. So the high fan-out routing helps with high fan-out nets. The incremental routing kind of helps more generally, but high fan-out nets tend to kind of really kill you for performance. And the paper kind of goes into more detail on kind of why that's the case. Okay, any other questions on what I've gone over so far?
Yeah, just a quick question. Could you just expand a little bit on why, like how were you able to basically blame the bad performance of AIR when compared to Quartus on the placement? Like,
Sure.
get a link.
Sure. So the idea is when AIR does its initial congestion oblivious routing, it is basically ignoring congestion. And so you're getting kind of best case minimum delay routes for all the connections in your circuit. So that kind of gives you a lower bound on what's achievable. So given VPR's placement, there is no difference between that lower bound delay and the final critical path delay that AIR achieves. So that tells us that given the placement, AIR is able to kind of match the critical path delay that is possible for that placement, even when it's produced a fully legal routing solution.
Got it, thanks.
Okay, other questions? All right. So now that we've kind of gone in depth on one of the optimization algorithms, I'm going to pop back out and kind of take a look at the overall VTR8 CAD flow and look at its kind of quality and runtime and a couple of the other enhancements that have gone into VTR8. So the first thing I want to look at are basically benchmark completion rates. So this is for the Titan benchmarks, those kind of large heterogeneous designs I mentioned before. And what we're comparing here are the results with VTR7, VTR8, and Quartus 18. So what we can see is that in VTR7, we were only able to route about 14 of the 23 benchmarks. So VTR7 was not able to implement all of these benchmarks successfully. In contrast with VTR8, we're now able to route all 23 of these designs. And that is actually comparable to what Quartus can achieve. Quartus is able to route 20 of 21 circuits that will kind of fit on an actual Stratix 4 device. And what we're showing down here is the kind of implementation produced for a number of the benchmarks. And this is showing the routing utilization, how many routing resources are used spatially within the FPGA. And I think it's just cool to kind of take a look at these, and interesting to see that the optimization algorithms are able to kind of figure out the structure of the circuit and produce different implementations that kind of exploit that structure to get us a good quality result. So we did also make enhancements to the packing and placement algorithms. One of the things we found that VTR7 did that was undesirable is it produced these highly interconnected and relatively unnatural clusters. So if our kind of basic netlist has some kind of elements that are connected to each other, those should probably go into the same logic block. But things that are unconnected to them probably should not. So what we found was that VTR7 tended to produce implementations like this, where some of the logic is kind of split among different clusters, which means that all of the clusters are really tightly interconnected. So we made a variety of optimizations to kind of alleviate this and produce more natural clusters. So we did things like avoiding packing unrelated logic into a cluster, focusing more on transitive connectivity, and deprioritizing the importance of high fan-out nets. And that allows us to produce more natural clusters, which turn out to be easier to actually place. We also made enhancements to the placer, in particular improvements to the carry chain swapping, and improvements to the swapping of blocks that are relatively sparse, think like RAM blocks or DSP blocks in the FPGA fabric. And so I think it's informative to kind of compare the implementation produced by VTR7 and the implementation produced by VTR8. This is on the DES90 benchmark. And what we can see on the left is that VTR7, because it produced all of these clusters that are so heavily interconnected, the placer has kind of crunched everything together in the center of the device. And so the routing utilization is extremely high in the center of the device. And in fact, in VTR7, this placement is unroutable. If we compare that with VTR8, because the clusters are more natural and we've made other enhancements to the placer, it's able to kind of spatially localize the connectivity of the circuit much more effectively. As a result, we see that the routing utilization has dropped significantly and things are more spread out. Okay, so let's take a look at the overall kind of runtime and memory footprint in VTR8. And so we're again looking at various metrics here. And 1.0 on these normalized metrics corresponds to the result achieved by Quartus 18. So what we can see is that VTR spends about 18% more time on packing than Quartus, but we have a very architecture agnostic and very general packer. So that's perhaps a reasonable trade-off. Our placement time is comparable to what Quartus can achieve, and we are able to complete routing significantly faster than Quartus. But overall, the kind of key takeaway here is that the runtime and memory footprint of VTR8 is comparable to what commercial tools can achieve. So runtime and memory footprint are only one side of the issue. It's also important to consider optimization quality. So again, normalized value here, 1.0 corresponds to Quartus, and we're looking at various resource usage and kind of optimization metrics. So we can see that VTR8 uses fewer logic blocks and DSPs than Quartus. We use slightly more small M9K RAM blocks, but slightly fewer large M144K RAM blocks. And we see that there is a quality gap. We use about 26% more wire length, and our circuits run about 20% slower than what Quartus can achieve. But for a set of open source tools, this is, I think, a pretty interesting result because it means that our quality is in the range of what commercial tools can achieve. Okay, so the last topic that I wanted to talk about is kind of some follow-on work that I did after VTR8, which is looking at how we can apply reinforcement learning to enhance placement. So before I get into that, I just want to talk a little bit about how I see reinforcement learning kind of fitting into the computer-aided design space. So when we're developing CAD tools, we are dealing with problems that have huge solution spaces. And that necessitates that we have to use heuristics in order to effectively find good quality solutions in a tractable amount of runtime. But the development process kind of goes like this. So someone who's a CAD engineer or a CAD researcher comes up with an idea, some way to enhance or improve an existing algorithm or some new optimization approach. Once they have that idea, they have to transform that into an actual tool. So they've got to go do some coding. But once they have the tool, they can actually go and evaluate their idea. They can run a bunch of benchmarks and see how well it does. But usually once you've done that evaluation, things don't look quite like how you would wish. And you end up having to go back and tune and tweak your heuristics until you get a good result. But the reality is that you can spend an awful lot of time in this evaluate and tuning loop. And this is a kind of an optimization loop where we have a human embedded inside the loop, and that makes it relatively slow. And it also means that the heuristics that we develop tend to be relatively simple. They tend to only consider a relatively limited number of tool parameters in order to kind of keep the whole problem tractable for a human to work with. Additionally, we usually don't have time to go in and investigate every single benchmark design. And so as a result, we also tend to tune for the average case behavior. So what I'm proposing is we take the human out of the loop and replace this kind of evaluate and tuning loop with a reinforcement learning agent. This will hopefully speed the process up because we're taking the human out of the loop. And the hope is that the reinforcement learning agent will actually learn better heuristics. It will be able to take in and exploit more information and consider more parameters than a human would be able to. And because the reinforcement learning agent is really embedded inside the tool, we should be able to have the tool adapt online to the problem that it's trying to solve to get better than average case behavior. Okay, so the context that I'm going to look at this in is in FPGA placement, and in particular, a simulated annealing-based FPGA placer. So a simulated annealing placer is trying to figure out where do we put the different components in our circuit on the FPGA device grid. And the way this works is it makes a set of moves to basically perturb the placement somehow. And whether that has improved or decreased the quality of the circuit implementation is used to determine whether the move that was done is accepted or rejected. And this is also dependent on something called the temperature, which allows us to do hill climbing out of local minima. Okay, so it turns out there are many different possible types of moves that you could make in an annealing-based placer. So the simplest one is some kind of random swap, where we just pick two blocks and we swap them at random. However, we could do something more intelligent. We could look at the circuit structure and say that if we have this block, we can look at what it's connected to, what the timing paths are going through it, and infer where would be a good location to move that block to. Now, in general, we could come up with a whole variety of different types of moves that could go all the way up to a more complex kind of placement algorithm itself. You could do something like a fast analytic placement for a particular subset of blocks in your design, for instance. Or you could perhaps formulate some kind of assignment problem that will optimize some metric and move multiple things at once. But if you're going to build this kind of system, a kind of system that uses simulated annealing as a framework for kind of selecting among the results of a whole bucket of different algorithms, effectively using simulated annealing as kind of a true meta heuristic, it's actually really complicated to think about how you would design and implement this kind of system. In particular, if we have a whole bunch of different types of moves that we could make, it's not obvious how often the different types of moves should occur. And if we think about it more, it seems quite likely that in certain situations, some moves will be beneficial and they may be less beneficial in others. And we also have trade-offs to make in terms of how well a move optimizes the design with its runtime. And so the approach that I took was to basically treat this kind of move selection problem as a reinforcement learning problem. And so here's an overview of what we actually built. So what we have is we have our reinforcement learning agent, and that agent gets to choose different types of moves to make. So in this case, we're using simple moves that will swap a logic block, a RAM block, or a DSP block. So the agent picks what type of move to make, and then the existing kind of tool infrastructure will evaluate that move and tell the agent what was the change in cost and was that move accepted or rejected. And so the agent will take in this information, and from that it will formulate a reward. In this case, for accepted moves, we use the negative of the cost. So if we decrease the cost of the circuit, the agent gets a positive affirmational reward and 0 otherwise. And so the agent has to kind of take care of 2 things in this kind of framework. It has to have some way of estimating the value of the different actions it can take, given the rewards that it's received. And it has to have some method to kind of pick an action given those value estimates. So let's take a look at those. So the first step is basically estimating these action values. So it turns out the value of these actions when we're doing something like FPGA placement is non-stationary. So what we do is we track this with a recency weighted average. So what we're showing here is the kind of progress in the optimization on the x-axis. So as optimization proceeds, we're going to the right. And what we're plotting are the Q values that in the reinforcement learning literature, that's kind of the action value, the value of taking a particular action at any point in time. And so if we zoom here into the beginning, we can actually see some interesting things. In particular, at certain points in time, the agent perceives that logic is the best type of thing that it can move. At other times, it perceives that RAMs are the best things it can move. At other times, DSP blocks. And so I think this is actually really cool because the agent is determining what type of moves are most productive online as the optimization is running. And what's cool about this is we didn't encode any of this kind of behavior into the tool itself. The agent is figuring it all out online. And this kind of oscillatory behavior of focusing on certain block types and switching to other ones is actually a heuristic that you can find in the research literature. But again, we didn't code that into our tool at all. The agent has figured that out for itself. So the second thing the agent has to do is it has to decide what action to take at a given point in time. And so there's this well-known problem in reinforcement learning. It's kind of called the exploration versus exploitation trade-off. And the problem is we have these estimates of how good these different actions are. We have to choose which action to take. So the approach that we take is what's called epsilon greedy action selection. This means that for some small fraction epsilon of moves, we will do a random exploratory move, just pick an action and try it, even if it's not the best one. But the rest of the time, we will take the greedy or best action that we think will give us the highest reward. And so what this plot is showing is runtime on the x-axis and quality, in this case, wire length on the y-axis, for various values of the epsilon parameter. And so what we can see is that as we decrease epsilon, basically make the agent more exploitative, we're actually able to significantly reduce placement runtime while basically maintaining the same optimization quality. Now, this is true up to a point. If we do no exploration at all, an epsilon of 0, then the agent just ends up doing the wrong type of move, and we get actually very poor quality. But we were somewhat surprised that we were able to make the agent quite exploitative and still maintain good quality. Okay, so let's take a look at how this compares to a hand-tuned tool like VTR8. So what I'm showing here is, again, placement time on the x-axis and wire length on the y-axis. And this blue point here at 1,1 corresponds to the VTR default parameters. Now, there are parameters that you can adjust in VTR that will kind of vary its runtime quality trade-off. One of these is the number of moves that you make per temperature. And with that, we can get this runtime quality trade-off curve. So if we take our enhanced move generator, and we just use a random agent, an agent that just randomly selects the type of move, we see that its runtime quality trade-off curve is shifted above and to the right, which means that it gets a uniformly worse runtime quality trade-off. But if we allow our reinforcement learning agent to kind of exploit the information it's received from the rewards, we see that the curve actually shifts below and to the right. So it gets a uniformly better runtime quality trade-off than VTR8. And so in particular, in a relatively high runtime regime, we get the same optimization quality in about 20% less runtime. But in the low optimization, the low runtime regime, we actually get the same optimization quality in about half the runtime. And the kind of insight here is that if you're making relatively few moves, then making sure that they're the right moves is very important. And that's where the reinforcement learning agent is very helpful. So in conclusion, we presented a reinforcement learning enhanced simulated annealing-based FPGA placer. It uses a reinforcement learning agent to control the move generator, and the agent learns online what types of moves are the most productive to make. And that this is able to improve the runtime quality trade-off, particularly at low runtimes. So in terms of future work for reinforcement learning-based placement, it would be really interesting to explore this kind of technique with more types of moves and more powerful moves. The reward formulation is relatively simple. It would be interesting to look at things like including the cost of the runtime of these moves. The agent currently is also fairly simple. The epsilon greedy action selection we presented is probably not the optimal choice. Some kind of soft max that allows us to kind of try a number of relatively good moves, it would probably be helpful. And the agent currently doesn't exploit any state information. It doesn't know anything about the circuit structure or statistics about the optimization process. So giving the agent that insight, I think, would further improve the results. And the learning process for our agent is also very simple. The agent currently learns online. It is not trained offline. So training the agent on, say, a set of benchmarks ahead of time would likely also improve the results. And there are a huge number of more powerful reinforcement learning algorithms, things like temporal difference learning and policy gradients in the reinforcement learning literature. So those would also be interesting to explore. And I think that this reinforcement learning type of technique can be applied to many different parts of the FPGA CAD flow. I think it's going to be really interesting to see how it can be applied there. So with that, I will conclude my talk. Thank you all very much for listening, and I'd be happy to take any questions.
All right, thank you for that wonderful talk. If you have a question, you can either post a message in the chat, or you can just shout out. So while we wait for people to maybe process this, do you have any insights on what algorithmic conditions must the CAD tool meet for RL to be attractive? Are there some preconditions of the structure of the problem or the nature of the algorithm that you need to have for this to be useful?
For this to be useful, I think you need something that can kind of give feedback to the agent, and that the agent can kind of then intervene in how the optimization process proceeds. So if you just kind of have a straight line algorithm that has kind of no choices to make, then reinforcement learning is not going to be helpful. So think something like a dynamic programming type of approach. If you have something where you're using some kind of, you make choices, most optimizations make some kind of choices. Making those choices in a better way, I think, is going to be a good place to apply reinforcement learning. As I said, many heuristics that we use right now are pretty simple. If you read the reinforcement learning literature, they take in huge quantities of information, different features to help the agent make its decisions. And I think we've got lots of interesting features. We collect statistics and things that would be very helpful for reinforcement learning algorithms. So I think if you have those kinds of things, then you can apply this kind of technique. Now, one thing that is also worth keeping in mind is the reinforcement learning agent that we used here is pretty simple. That is an advantage because we are calling this reinforcement learning agent right in the middle of the annealing-based placer. So it's like right in the inner loop. So having a cheap, low-cost agent is helpful. As you go to building these more complex agents, you would probably need to be a bit more careful about when you kind of ask the agent to do something, because the runtime cost of doing that becomes higher. Okay, so one of the questions from the chat, do you think about overfitting issues for agents? That is definitely a consideration. I don't think it's an issue in the results I presented. As I said, the agent that we currently have learns online. So it basically starts from scratch whenever you run the placer. So it's not going to overfit to any like previous training data or anything like that. Additionally, the agent currently kind of focuses on relatively short timescale phenomena. It's kind of, I guess I would say, relatively forgetful. That's helpful for kind of keeping it exploring and trying new things. So I guess in the current formulation, I don't think overfitting is going to be an issue. Although certainly as you, if you were to kind of take this forward, you know, there is, I guess, sorry, I lost my train of thought. As you take this forward and you kind of do things like offline training, then I think you do need to be careful about overfitting, because you know you probably want to come up with a general technique that will work for a large number of architectures, a large number of benchmarks. So you would have to be careful about overfitting if you were doing things like offline training. Although I will say, you know, if you're a commercial vendor and you want to apply this kind of approach, overfitting to your target architecture is probably not a bad thing. You know, the Intel tools probably don't need to optimize for Xilinx FPGAs, but VTR is somewhat of a different case.
I think there's a follow-up in the chat as well.
Okay, so regarding STA, how could it? Yeah, okay, so I didn't talk about the static timing analysis, but another thing that I did in my research was build a static timing analysis engine called Tatum, and that is the static timing analysis engine used in VPR. I was fairly careful to build Tatum as a library, so it operates only on a kind of abstract timing graph that the application has annotated delays on. So I think the question is, you know, could you apply Tatum to a pre-synthesis netlist? I think you definitely could. If you have the netlist structure, you can build a timing graph from that, and you would need some way to estimate the delays. But if you have those delays, you can annotate them on the graph, pass them to Tatum, and Tatum will give you back the STA results. And Tatum is used both in VPR and it's also used in the CGRA project, which is a project for CGRA research. So it is definitely retargetable to different tools.
Okay, thank you. We have time for more questions.
Hi, Kevin. Danny from DC here. So I'm actually new to VTR and I have a question there. So FPGAs nowadays, they're very heterogeneous. We have domain-specific FPGAs with like hard blocks that perform like matrix multiplications, for example, like they help you in matrix multiplications. So which kinds of blocks or like FPGA characteristics of those new heterogeneous FPGAs would we not be able to describe using VTR, or is VTR really like a tool that I can do whatever I want there now?
It kind of depends at the kind of level of, it depends somewhat on the level of abstraction. So if you're taking the case of like, I want to put, like, I don't know, maybe if you're familiar with NVIDIA, say like the Tensor Core equivalent into an FPGA, you can definitely model that. You would basically say, here is the block, here's how big it is in the grid, here is its area, and the delay of the timing paths through it. And then you can plunk that down into the VTR architecture, and the rest of the FPGA will be built around that kind of to your specification. The part that kind of is more challenging is kind of how do you put that into the netlist? So that's kind of a problem of kind of the inference problem. Like, are you going to take someone's HDL code and just infer that this fits in your tensor core? That's more challenging to do. There is basic support for that in the Odin tool, but most people who are doing that kind of research, what I've seen them do is basically kind of manually instantiate that in their Verilog and say, like, I'm going to put a tensor core here and write my Verilog around it. And that's the approach I've generally seen been done for that kind of technique.
Cool, thanks.
I had one question about the very first section of your talk about architecture.
Mm-hmm.
So last week we had, a couple of weeks ago, we had someone from Penn talk about partial reconfiguration or dynamic partial reconfiguration, and the kind of support you need was a little tricky to get going in VTR. So I was just wondering, maybe not you because you're graduating soon, but someone else in Vaughn's group, are they looking at trying to add PR support as sort of a first-class citizen in the XML architecture?
I'm not aware of any plans for that, at least from like a code kind of architecture perspective. We are kind of continuing, and people are continuing to work on making VTR kind of more controllable, I would say. So being able to do things like lock down, like you have a partial placement for your design, you want to lock parts of it down. And those kinds of capabilities, the ability to kind of load that partial placement and replace part of the design, those are the kind of capabilities that I think would enable these kinds of partial reconfiguration design flows. But I don't know of any plans to kind of bake that into the tool itself. I think what we would probably prefer to do is kind of make the tool controllable and kind of let people build their own flows using the kind of the controls that are there.
Makes sense. Are there any other questions? Okay, if not, then let's thank Kevin for that wonderful talk again. And I will see everyone next week where Professor Jason Anderson and his team are going to talk about CGRME. All right, thank you. See you next week.
Thanks, everyone.